Assalamu
السلام.
Okay, Shiva, we started chapter 26 last time, and we started the discussion of the convective mass transfer and we solved example last time to find the convective mass transfer coefficient Kc. Today we'll continue the discussion on something related to Kc, the convective mass transfer coefficient, and we'll start with some analogy between the momentum, heat, and mass transfer. And the energy we are discussing is for the diffusivity. So you have something from CH804, something called momentum diffusivity. You heard about it? Have you heard about momentum diffusivity?
Not really.
No, I don't think so.
Okay, have you heard about the kinematic viscosity?
Yes.
Yes.
It's the same. Okay, kinematic viscosity is the same, which is mu over rho. So nu is mu over rho, which is the kinematic viscosity, as dimension is length square per time. Have you heard about thermal diffusivity? Not yet, right?
Yes.
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 In heat.
Yeah, okay. So the thermal diffusivity is defined as K, the thermal conductivity, over rho Cp. Cp is the heat capacity, a specific heat capacity. And also the dimension or the units of the dimension of thermal diffusivity is also length square per time, same as momentum diffusivity. And we have in this course mass diffusivity, which is DAB, and it is length square per time. So you see that these three quantities, momentum diffusivity, thermal diffusivity, and mass diffusivity, they have the same dimensions: length square per time, length square per time, length square per time. So there's analogy between them. And also in terms of the profile, we have this one for the momentum or the velocity profile, or we call it the hydrodynamic boundary layer. This one we'll call it the concentration boundary layer, and the thermal boundary layer. So at this point you have the velocity is 0, and at the center line here you will have the maximum velocity, and then from this point upward the velocity increases, or in this direction decreases. We have also something called concentration profile, we'll discuss later on, and depending on the mass transfer direction. So if it is, for example, from the bulk to the surface, the difference, this is the gradient force, okay, or the driving force. So CAS minus CA, CA is changing along the way here, and CA is constant, CAS. So if your mass transfer coming from this side, as you go down, the difference will be less, because CA will decrease along the downside here. If your mass transfer coming from this side, CA will be also decreasing upward. Okay, so this is the driving force. This is the driving force for thermal conductor, for the heat transfer, and this is the temperature at the surface. So we have this is the driving force, is function of time, function of y, and this is the driving force for heat transfer, function of y, and this is the velocity profile, which is also function of y. Okay, so now let's go back to our example we solved last time. We had this system where we coat the surface with a solvent A plus solid polymer, and then we evaporate the solvent and leave the polymer coating on the surface. And this process, if you remember, took like 45 seconds to evaporate all the liquid solvent from it. So now we did balance last time on the amount of solvent inside the system. So inside the coating here, the solvent A changing with time, because it was initially 0.35 gram, and then at the end, after 45 seconds, it reaches 0 here. So when you do balance on the coating for A, the balance will be unsteady state because you have negative accumulation. A is removed from the coating. But we will do balance on the borderline here between the coating and the bulk here, or the gas phase. Remember that we said that the pressure, the vapor pressure of the solvent A at the surface here is constant. So it means that CAS is constant. So if you have CAS constant at the surface here, means that you have no accumulation. There's accumulation inside or negative accumulation, but on this line here between the two phases, the gas and the solid phase or the liquid phase inside the coating, is steady state. Okay, once the molecules of A reach the surface here or the interface, they will transfer, they will not stay here. So there's no accumulation for A at the border line here. And if you do balance using the general mass balance equation, which you have always to use, this mass balance equation, whenever you have something like this, whenever there's mass balance in the problem, always start with it. If you don't start with the general mass balance and simplifying it and then solving it, you will lose some points. So for this one, we'll do balance at the interface. So we'll have the general mass balance, input minus output plus generation minus consumption, equal accumulation. Since we said that CAS is constant, so there's no accumulation here, and the accumulation term is 0, and no reaction, so consumption and generation are zeros. So we have input minus output equals 0, or input equal output. So whatever, and the mass direction in this way. So you have the input coming from the coating and the output to the surrounding layer. So the input coming from here through in this coating, we don't have any agitation. There's no agitation in this coating here. So mass transfer in this coating is by diffusion, and this is the flux coming from the coating at the point here where Y is 0 at the interface between the coating and the air or the surrounding gas. So at Y equals 0, the flux coming from this one is minus DAB times DCA times over dy. So this is the flux if you multiply it by area, and you get molar flow rate. If you multiply by area and molecular weight, you get mass flow rate. This the balance here, okay, since we have no reaction, if you do mass balance, it will be also conserved. So moles in should equal moles out. So the moles entering here should equal the moles leaving, and the moles leaving we can get from the convection, because from this point onward we have mass transfer by convection. Inside the coating is by diffusion. And the flux, the convective flux, as we discussed before, is Kc times the gradient force, CAS minus CA infinity in the bulk. So now we can equate, since if you multiply by the area, you multiply also by the area, so the area will cancel. So the flux coming from the coating will equal the flux leaving the interface here. So this Kc times CAS minus CA0 will equal minus DAB times DCY over DCA over dy at Y equal 0. And then, as you know, that CA is constant, so the derivative DCA minus CAS will equal the derivative of CA. So if you just put brackets like this one and insert any constant here, the derivative will remain the same. So DCA minus CAS will be the same as DCA. Any constant here will not affect the derivative because the derivatives of the constants are zeros. So now we have this equality here at Y equals 0. dA minus dAB times the derivative of CA minus CAS over dy equal the convective flux. And if you divide both sides by CAS minus CA0 and dAB, you get minus DCA over CA minus CAS over dy at Y equals 0 over CAS minus CA infinity will equal the ratio of the convective mass transfer over the diffusive mass transfer coefficient. If I divide here by, or multiply by L here and L here, nothing changed because you multiply by the same quantity. And instead of putting it in the numerator here, I put it as a denominator for the denominator. It will go up later. So Kc times L, and L is the length, the characteristic length of the slab here. So over DAB will equal minus D of the CA minus CAS over dy at y0 over this quantity CAS minus CA infinity over L. So this is okay the ratio of the gradient force over or the concentration gradient over the change in y, and this is the concentration gradient in this region here over L. This one we call it Sherwood number. So Sherwood number is Kc times L over DAB. Yes, Hamad.
Yes, doctor. So you multiply by L to make it this number.
We want to reach this number, yes. We want to reach Sherwood.
Okay.
Number. So Sherwood number now is defined as Kc times L over DAB. And from chapter 25, okay, this one I can put it as 1 over DAB because denominator of denominator will go to numerator. So this will be like this, 1 over DAB over 1 over Kc times L. And from chapter 25, the reciprocal of the DAB is called molecular mass transfer resistance. And the reciprocal of Kc times the characteristic length, in that case, now it's L, is called convective mass transfer resistance. So Sherwood number is basically the ratios of the convective, of the diffusive mass transfer resistance or molecular mass transfer resistance over convective mass transfer resistance. In heat transfer, okay, we define Nusselt number as thermal conductivity or conductive heat transfer resistance over convective heat transfer resistance. You remember this, right? You reached that point?
Yes, doctor.
So this Sherwood number in mass transfer is analog to the Nusselt number in heat transfer. We have another number called Schmidt number in mass transfer. The Schmidt number is momentum diffusivity over mass diffusivity. So if you go back to this here, momentum diffusivity over mass diffusivity, so you divide this rho mu over rho over DAB, you get something called Schmidt number, or you can use the kinematic viscosity instead, mu. So this is momentum diffusivity over mass diffusivity. We call it Schmidt number. If you divide momentum diffusivity over thermal diffusivity, you get something called Prandtl number. You know this? So if you go back here and divide momentum diffusivity over thermal diffusivity, basically rho mu over rho divided by K over rho Cp, you get something called Prandtl number. You heard about it?
Yes, doctor.
Yes.
Yes.
Mhm.
So these are somehow, the Sherwood number is analogous to Nusselt number in heat transfer, and Schmidt number is analogous to Prandtl number in heat transfer. We have also the ratios of the thermal conductivity, the diffusivity over mass diffusivity. So these are here like alpha over DAB, and it's also equal to K. K is the thermal conductivity over rho Cp DAB. This one we call it Lewis number. So Lewis number is the ratio of thermal diffusivity over mass diffusivity. Okay, we'll be using Sherwood number and Schmidt number a lot in this chapter and chapter 28. And we have example here to illustrate the difference in Schmidt number between between gas phase and liquid phase. And this example, we're using methanol as the solute. So methanol evaporate or we have methanol vapor in air. The temperature of air is kept constant at 308 Kelvin or 35 degrees Celsius, and the total pressure is 1 atmosphere. In the second case, we have methanol dissolved in liquid water. So we have two different phases. The first one is gas, the second is liquid, and methanol diffuses in air and liquid water. Okay, the temperature of liquid water also keeps the same as for the air, which is 308 Kelvin. What we want to find Schmidt number for this system, methanol in air at this temperature and pressure, and methanol in water at the given temperature. To do that, what we'll need, Schmidt number, as you know, is defined as kinematic viscosity, mu over dAB, or mu over rho dAB. So we need the diffusion coefficient of methanol in air at the given temperature, and also methanol in water at the given temperature. And we need the kinematic viscosity mu. So for methanol in air, we have from appendix J, we have the diffusion coefficient of methanol in air at 1 atmosphere and 298 Kelvin. So from there, the diffusion coefficient of methanol, and let's call methanol A. So the diffusion of A in air is 0.162 centimeters square per second. This is at 298 Kelvin and also 1 atmosphere. But we want the diffusion, or the process is carried out at 308. So we have to extrapolate to this temperature. And according to what we discussed in chapter 22, this is the extrapolation equation. So dAB at the original temperature and pressure, okay, you multiply by the ratios, okay, T mu, or the nu T over the T reference, times the P reference over the nu P. The pressure remains the same. The pressure remains the same, so it's still 1 atmosphere. So this will be 1, and the ratio here of omega D will be almost 1, because the temperature difference is not huge, as mentioned in chapter 22. When the temperature difference is less than or equal to 10%, the difference in omega D will not be huge, so you can approximate it to 1. And if you check the difference in temperature is about 3% difference, so this will be almost 1. So we can also ignore it and put it as, or approximate it to 1. So it will be just the ratio of the temperature. The ratio of the pressure is 1. The ratio of omega D is 1 also. So the new dAB, or the dB at the given temperature 308, will be 0.17 centimeters square per second. And the kinematic viscosity of air from appendix I, okay, is, and at the same pressure and temperature here, 1 atmosphere and 308 Kelvin, it will be, if you look into appendix I for air, it will be 0.164 centimeters square per second. And you divide the kinematic viscosity over dAB, it will be 0.966. So this is Schmidt number. Schmidt number for methanol in air at this temperature and pressure is 0.966. For Schmidt number for methanol in liquid water, we have to find the diffusion coefficient of ethanol in water. And from chapter 22, we have the molar volume of methanol at normal boiling point is about 59.2 centimeter cube, sorry, per mole. The kinematic viscosity of water at the given temperature from appendix I also is 7.24 times 10 to the 1-3 centimeters square per second, and the viscosity is about 0.7198 Cp. So now we can calculate the diffusion coefficient using one of the correlations we discussed in chapter 22, and we're going to use hydrochloric correlation. It's given by this 13.26 times 10 to the 1-5 times mu of the solvent, which is water in this case, raised to power minus 1.14, times the molar volume of the solute, which is methanol, raised to 0.589. We get the diffusion coefficient of methanol in water at the given temperature here, 308, is 1.744 times 10 to the 5 centimeter square. This should be square, centimeter square per second. Okay, so correct this in your book. It should be centimeter square. Then the kinematic viscosity, we got it from appendix I for water. It is 7 0.424 times 10 to the power negative 3 centimeters square per second. You divide them, you get 415.3. So Schmidt number for methanol in water is 415.3. And this is the normal case or the typical case, that Schmidt number at the same temperature in liquid phase is usually several times higher than the Schmidt number in gas phase. So this is like 420 times higher than the Schmidt number in air at the same temperature. Why? Because usually the kinematic viscosity of gas phase is higher than the kinematic viscosity of liquid phase, and the diffusion coefficient in gas phase is higher than the diffusion coefficient in liquid phase. So we get Schmidt number usually for liquid phase several times higher than the Schmidt number in gas phase. Okay. Any question? Okay, so let's move to dimensional analysis of convective mass transfer coefficient or convective mass transfer. So we have to use something called dimensionless analysis. Okay, so we obtain some dimensionless parameters or numbers, and then we expect or predict a correlation between, or functionality, for example, how the one of the dimensionless parameter will depend on the other. So it's like prediction of which variable or which dimensionless would depend on which other dimensionless parameters, and then we can run experiments to collect data and then establish or formulate a correlation to relate these dimensionless parameters by each other, and from that we can predict the convective mass transfer coefficient. And we'll do it for two cases. The first case is for forced convection, and the second one natural convection. Forced convection, I'm not sure if you come across this one in heat transfer. Have you come across forced convection and natural convection in heat transfer?
Yes, doctor.
Yes, doctor.
Okay, so you are familiar with these terminologies, right?
Yes.
Yes.
So for forced convection, you have velocity there. So there velocity in the system. So you're pumping, or you manipulate the or you interfere with pumping or whatever. So you provide certain velocity there. Natural convection, there's no velocities, just by some natural forces. And we'll be using something called Buckingham method. Have you heard about it? In
Yes, doctor, in 204.
204, yes. Should have heard about it in 204. Okay, شباب ذكرته ولا لسه؟ In 204.
Yes, I think we
So
come across.
Buckingham method, I'm sure you discussed in CHE 204. So we'll go through this method quickly because you should have come across it in 204. And we'll start with this one. Okay, the forced convection. For forced convection, we'll have velocity. Okay, so there will be, we'll take it for a pipe, circular pipe or tube. So you have fluid flowing at certain velocity in this circular tube under forced convection because we force it to flow. Okay, we force it to flow, okay, through pumping, for example. And the first step is to define the effective variables. So for this analysis, you have to, the dimensionless analysis, you have to define variables, the effective variables. And for this kind of process, okay, for fluid flow in a circular tube under forced convection, we'll have the diameter of the pipe or the tube is D. We'll use the symbol D for it. Fluid density, because the fluid is flowing there, okay, and it will contain, for example, solute. Let's say the solute transfers to the wall of the tube, okay, from the fluid to the wall of the tube. So we'll have the fluid density will play a role in this convective mass transfer. Also, the fluid viscosity, mu, the density is rho, the viscosity is mu, will also play a role in this convective mass transfer process. The velocity, because it's forced convection. Diffusivity, also a factor here, because as we discussed in chapter 24, the Kc, convective mass transfer coefficient, is function of diffusion coefficient. And also Kc, so the overall convective process, also function of the convective mass transfer coefficient. CMT is convective mass transfer. And the dimension of diameter, as you know, is length, is dimension of length. Dimension of the density is mass m over length cube, or m times length cube inverse, or to power minus 3. Viscosity is mass over length over time, or m times L to power minus 1, T to power minus 1. Velocity is length over time, or L times 10 T to minus 1. DAB is length square over time, or L square times T minus 1 to power T to power minus 1. And Kc is length over time, or length to time multiplied by time to power minus 1. So these are the dimensions. So the first step, we define our effective variables. These are the variables that control convective mass transfer under forced condition. And this, the symbols we are using, and these are the dimensions of the quantities or the variables. So we have 6 variables. Okay, the diameter, velocity, so diameter, fluid density, viscosity, velocity, diffusivity, and mass transfer coefficient, convective mass transfer coefficient. And the dimension, we have length, mass, and time. So according to Buckingham method, we define we determine the number of dimensionless group. Okay, and it's defined like this: number of dimensionless groups is number of variables minus number of dimensions. We have here 6 variables and 3 dimensions. So we'll get number of groups, in this case 3, and we'll call them pi1, pi2, pi3. So the next step, the third step here, is to define k variables. Okay, number of k variables should equal the number of groups. So we have 3 groups, we should have 3 k variables. Yes, Hatim.
Doctor, what about temperature and pressure?
They are
The variables.
they are captured here in the density and the viscosity, and also in DAB. Because density is function of temperature, viscosity is function of temperature, and if you have gas, also density is function of pressure, and DAB is function of pressure if you have gas. Okay, so they are captured there indirectly. So you have to define then the k variables, and the k variables should be the same as the number of groups. So let's define our k variables as Kc, because we are talking about convective mass transfer. So Kc is one of the key variables, okay? Because you are talking about convective, so convective mass transfer coefficient should be there, should be one of the key variables. And since you are talking about forced convection, velocity should be also a key factor, okay? So velocity also a key factor. And the third key factor for forced convection is mu, because this one is related to the velocity also. If you have highly viscous material, you will need high pumping, okay, high energy to pump it. Okay, so this velocity also one of the viscosity is also one of the key variable, because it affects the mass transfer under forced convection. These variables are more important than diameter. Of course, this is still variable there, and still is important. The density is still important. Diffusion coefficient is still important, but these are the key, the most important ones, the 3. Then we define dimensionless group, as we said, pi1, pi2, pi3. All these are dimensionless, so their dimension should be, so they should have no dimension. Okay, so we take the remaining variables, and every time we multiply them by one of the key variables. So we start with multiplying the 3 variables by Kc, then by mu, then by viscosity, by velocity. This will be the first number, the second number, and the third, or the first group, second group, third group. And now we see that we put here power A, power B, power C. This is D, E, F, G, H, I. And then we analyze. So there will be the dimension. We know the dimension of diameter, as according to the table here, is length. So we put length there. So it is length to power A. And the dimension of density is kilogram times length to power -3, and also raised to B. Dimension of DAB is length square times T to power -1 raised to C. And the dimension of KC is length times T to power -1. For the second group, it will be D here. Okay, it's dimension of length to power D, dimension of SAM. This one will be the same as this, as this, as this. What will change is the last one. So we'll have, but we put different power because this might be the dimensions might, overall dimension might change at that of this number will be dimensionless, but with this, because this one is not the same as this one, dimension of mu is not the same as KC, so you expect that the power here might change. So D, E, F, and this the mu m times L to power -1, T to power -1, and this one again power G, power H, power I, and this is L times T power -1. We said these groups are dimensionless, so their dimension for L is power 0, so they have L to power 0, M to power 0, T to power 0, and these are our dimensions, L, M, and T. And H1 should be raised to power 0, because when you raise it to power 0, what will be this? Anything raised to power 0, what is it? When you raise anything to power 0, what you get? 1. So this will be 1 times 1 times 1. So it's dimensionless. You get 1 here, 1, 1, 1. Okay, and this, the summation of these powers for L should be 0, because the power here is 0 and should be equal. Left hand side and right hand side should equal. So if you add up L minus 3B plus 2C plus 1, you should get 0, because the dimension of L's here, L here should be 0. Dimension of M should be 0. Dimension of T should be 0. Same for this this relations here, and this also. So now we do the analysis of the dimensions for the proposed groups here. We know that left hand side the power or the dimension is 0 and should equal the dimension. The dimension on the left hand side should equal the right hand side. And then we solve for the constants from A to I. Starting with pi 1, we have on the left hand side, we have 1, means that M to power 0, L to power 0, T to power 0. And this should equal here L minus 3B plus 2C is coming from just adding the powers here of L. We get A minus 3B plus 2C plus 1. And M to power B, T to power minus C minus 1. We start with the easy one to solve, because we know that M has a power of 0. So B should be 0. And then this is the next easy one. We know that the power of T should be 0. So minus C minus 1 should be 0. And this means that C should be minus 1. Minus 1 times minus is 1, plus 1, minus 1 will be 0. So we know C is minus 1 and B is 0. We insert them in this relation. So A minus 3B plus 2C plus 1 should be 0, and solve for A, it will be 1. And then we go back to our relation. Our relation here, D to power A, rho to power B, DAB to power C. Okay, so now we know that B is 0. B is 0, so rho to power 0. L is A is 1, so D to power 1, and C is minus 1, so DAB to power minus 1 times KC. This would be 1. Rho to the power of 0 is 1, so we'll have D times KC over DAB. And this one is called Sherwood number, as we defined here. Sherwood number, if you go back to this point, Sherwood number is KC times L over DAB. And if you're talking about circular pipe, you replace L with the diameter. So we get the first dimensionless number, which is Sherwood number. Okay, and we do the same for pi2. Okay, so for pi2 we have also the power on the left hand side should be 0, and also on the right should be 0. We have, if you go back here, pi2 equal DAB, D to power D, rho to power E, and DAB to power F times mu. And this should be LD minus 3E plus 2F minus 1 should equal 0. M to power E minus plus 1 should be also 0. T minus F to power minus F minus 1 should be also 0. So we use this to find the second dimensionless group, which is, or number dimensionless group, which is pi2. So it will be for M E plus 1. So this should be E should be minus 1. Yes, Hatem.
Doctor, if I choose different key variables, will I reach the same
We'll come to that.
number?
Yes, we'll come to that later. Okay, so now M is E plus 1. Power of M is E plus 1. So you should get this 0 as M here is 0. Power of M is 0. So means that E is minus 1. This one also the power should be 0. So means that F is minus 1. And when you solve for this, this will be minus 1, and this will be minus 2 times minus 1. So you solve, you will find that D, okay, D, if you go back here, okay, should be power of, okay, 0. So D will be 0 there. So you get mu over rho DAB, which is the same as we defined Schmidt number. So from the second dimensionless group, pi2, we get Schmidt number. From the third, we analyze it. We'll find that the third one will be same analysis as we did with the pi1 and pi2. We get mu pi3 equal D times F times V over DAB. Now we come to Hatem's question. Okay, if I change these variables here, okay, I don't use these or any of these, I will still get dimensionless number as long as, let's say I put, for example, D here instead of V. Okay, D instead of V. Okay, if I manage to put it in a way that it is dimensionless, I will get a number, but not necessarily the one we are looking for. So the selection of these key variables and these variables to give us the numbers we are looking for. If you change, you will get a number, but not the one we are looking for. Okay. Okay, Hatem.
But doctor, is there a criteria to choose the key variables?
You analyze based on what you're looking for. Okay, we know from here that Sherwood number, okay, is function of these things. Okay, and Schmidt number is also important from the analogy with heat transfer. Okay, so we need this one and we need this one, and probably also something else which is related to the velocity, which will come to it. Okay, so you should have prior knowledge of your system before you do the analysis. So you know that we are looking for some numbers, but we need to relate them. Okay, we need to reach a conclusion how they are related. Okay. Of course, as I said, if you vary, if you don't choose if you vary the quantities here, if you vary the quantities here and quantities here, you will get a number, but might be helpful, might be not for your system. If you come to that number and you find that it's not helpful, you go back and change until you get the number you are looking for. Okay.
Okay.
So now, for example, we got this number here. Okay. This one is also dimensionless. D has a unit of length, V has a unit of length per time, and this will be length square per time, and this will be length square per time. So this is dimensionless number, but it's not a common number. We don't know this number. There's no number called like this. Okay, so or this will not give us the number we are looking for. Okay, so this is dimensionless quantity, but not a common number. Okay, so to make it a common number, we have to make some arrangement, and we're going to divide pi3 by pi2. So if I divide this by this, you have d times v over dab over mu over dab. Dab will cancel with dab, and you will get d times v times rho over mu. So you divide pi3 pi3 by pi2, you get this one. Rho times dv times d times v over mu. What is this number?
Reynolds number.
Reynolds number. Okay, so we are looking for common numbers. Okay, that will help us. We can still use this, but it's better to have a common number that is known. Okay? So if you come to a number that is not common, you can do some rearrangement to get a common number. Yes.
Doctor, so this is like a derivation or how we found Reynolds and the two numbers, SC and the Schmidt number. Right.
This is based on the dimensionless analysis. So we have, I said we have these variables, okay, and these are their dimensions. So we need to get some dimensionless group, okay, based on these numbers and these variables, and these groups will be dimensionless as mentioned here, okay, but these groups also should give you some common numbers. Okay, you can, as I said, keep this number as is. This dimensionless, okay, but it's not a known number. Okay, so we cannot say this is like X or Y or what, or like, for example, Sherwood or Schmidt or whatever. We need something that when you tell someone this is Schmidt number or Reynolds number or Sherwood number, they know what you are talking about. Did I answer your question?
Yes, Doctor.
So we got this one. Now we see that we started from the same table here. From the same table, we just chosen 3 variables as key variables, and the others are not a key variables. And then we get these 3 numbers: Sherwood number, Schmidt number, and Reynolds number. Based on this, since we are just using, okay, almost, yeah, all of them, this, for example, this Sherwood number, we obtain it using this first relation. So it has DAB. So if it has, for example, one of or 2 of these variables. Same here, same here. Okay, so these are this number you obtain for pi2, pi3, pi2, pi3. They are expected to be related in certain sense. So they are related. Sherwood number, and Schmidt number, and Reynolds number. Based on the analysis we did, we expect that these 3 numbers should be related when you talk about forced convection. So these 3 dimensionless groups or numbers are related. How related? Okay, we can say that Sherwood number, for example, function of these 2, Schmidt number or Reynolds number, or Reynolds number is function of Schmidt number and Sherwood number, or the other way. So they are related by certain equations or certain correlation, but we don't know the exact correlation. So Sherwood number, we know that it is function of Schmidt number based on this dimensionless analysis, and Reynolds number. But how related is it? For example, Sherwood number, Schmidt number equals Sherwood number plus Schmidt number. Is it Schmidt number to power 2? Is it to power 3? What is the exact equation here? We don't know, but we know that they are related. So we know that they are related. Now I can go to the laboratory and conduct experiment by varying Schmidt number and Reynolds number only. Of course, when you change Reynolds number, you have to change either the density or the velocity or the diameter or the viscosity. Okay, and Schmidt number, you change the diffusion coefficient or the viscosity or density. So we change Schmidt number and Reynolds number, and we record the value of Schmidt number. Okay, because if you have if you vary Sherwood number and Schmidt number, you can also find a value for Sherwood number. So we collected the data for Sherwood number and Schmidt number and Schmidt number and Reynolds number, and relate them to Sherwood number, and then we can establish or create a correlation that we can use later on. So we use a correlation, and at any Reynolds number or Schmidt number, we can calculate Sherwood number. Just we run some tests, some experiments to establish this correlation, and then we use it, generalize it. Of course, when you use correlation, you should use it with caution, because it might not be valid for other scenarios, but usually we generalize with keeping in mind that there might be some errors. Okay. Now for the second scenario, the natural convection. Yes.
How did you conclude that the Sherwood is the main one and the other two are independent or depend on it?
No, I said, listen to me carefully. I said you can say that Schmidt number is function of Sherwood number and Reynolds number. Reynolds number function of Sherwood number and Schmidt number. You can put the relationship as you want. Okay, but we are interested in this more, because if you go back to these numbers, okay, this Reynolds number doesn't contain Kc. This Schmidt number doesn't contain Kc. The only one that contains Kc, the convective mass transfer coefficient, which we are interested in this chapter, is Sherwood number. Okay.
Yes,
but
clear, doctor. So
you can put it in any way you want.
Yes, we focus on one. Thank you.
Okay. So now we talk about
Doctor,
yes.
I'm sorry, are they related by a number or like a function?
There will be equation.
Variable.
Later on, we'll come to an equation here. So there will be a equation. So for example, Sherwood number, as I said, it could be, for example, Schmidt number plus Reynolds number, or Schmidt number square plus Reynolds number cube, whatever. There will be a question. Okay.
Okay.
Okay, the second scenario is natural convection, or mass transfer, convective mass transfer by natural convection. When do we have natural convection? Here we have forced convection. So you pump the fluid, so you have velocity there. Okay. But sometimes mass transfer, convective mass transfer might take place by just natural convection. Like for example, one of the things that's very known to you, I believe, is that you know that when air, for example, heats up, it goes up, right? And the cold one will flow down. You know this?
Yes, doctor.
Yes.
So there, for example, if the for example the air near the surface of Earth gets warmer, it will be less dense, so its density will decrease, and one layer of air above it will be at higher density because it's colder. So there will be exchange. The colder one will go down and the hotter one will go up. So this is natural convection. So you carry all the phase, not just the solute. In diffusion, if you remember in chapter 22, we said just the component, the solute transfers. Okay, so if you have the air at uniform temperature, uniform pressure, and for example, at certain location, it contains, for example, water vapor, the water vapor will diffuse in the air if the air is stagnant and transfer to the other locations. So that is just by diffusion, not convection. But here, no, the whole phase, including the not the solute, the solvent as well, if we call air is solvent. So the air moves up with any solute in it. If you have, let's say, methanol in the air near to the surface, then it will also float up with air. So that is natural convection, not diffusion. So natural convection usually occurs because of temperature differences, and temperature differences creates the variation in density, and therefore, when you have variation in density, the dense one will flow down, and the lighter one will flow up. Sometimes might be because of big variation in concentration. Like for example, if you have just two tanks, one under little bit vacuum, is not at the same pressure as the other one. When you open it, there will be exchange between these two tanks because of the pressure gradient. So that is also might cause natural convection. Because again, the concentration and the density gradient. So in these cases, we don't have velocity. Okay, we don't pump the liquid or the fluid. It just takes place naturally because of the variation in density or concentration, big concentration. So we're going to deal with it as analyze it for the for vertical plane or wall. So we have a wall which is erected vertically, and we have fluid adjacent to it, flowing but naturally, not by force. Okay, it's not by convective force. So we'll take the length, the characteristic length of the wall as L, the fluid density as rho, the fluid viscosity as mu, and here one of the important factors is buoyancy. Okay, if why we come back to the air, why it flows up, the hot air, because of the something called buoyancy force. So the buoyancy force is very important here in natural convection, and the driving force for buoyancy is the change in density and gravity. So G times delta rho. If you have no change in density, there will be no buoyancy. Okay, if you have change in density and change in gravity as well, this will also allow the buoyancy force to take place. And the diffusivity and the convective mass transfer. So the dimensions here, L, m times L to the power minus 3, m times 2 to the power minus 1, t minus 1, and the buoyancy is m mass times L to the power minus 2 and t to the power minus 2. So all the old numbers here, just we change this one to d or L, because we have plane, not circular pipe, and we change the velocity with this one. Mu, rho, DAB, and KC the same. So we have 6 variables, 3 dimensions again, L, M, and T. Using Buckingham method, we will have 3 groups, and they are number of variables, number of dimensions. We call them also pi 1, pi 2, pi 3, and we define key variables. Now we define 3 because we have 3 groups. Again, we're talking about convective mass transfer. So mass transfer is a key here. Convective mass transfer is a key. And from here, this is the driving force for buoyancy. If you have no change in density or gravity, if the gravity is 0, then you have no buoyancy force. So you should have gravity and you should have change in density. So this one, gravity and delta rho, the product is K factor. And also the density is also factor. So these are the key factors, and the remaining 3 is L, mu, and DAB. We'll do similar analysis. First group, okay, we multiply the 3 non-key variables by one of the key variables, Kc, and then this 3 by another key variables, rho, and then by G times delta rho. Okay, and we analyze the dimensions. So we should have the dimension of L on the right hand side 0, the dimension of M 0, or the power of M is 0, and the power of T also 0 for all these numbers. So we start with the first one, pi 1. Again, the power of M should be 0, the power of L should be 0, power of T should be 0. And if you go back to this one, you have just M here, not here, not here. So M will be to power B, means that B should be 0. And then you have T to power minus B minus C minus 1, means that minus C minus B should, minus 1 should be 0. Okay. So minus B minus C minus 1 is 0. And B already got from, you got already B from here. So you get 0 minus C minus 1. So C is minus 1. And then you solve for L or for A. So power of L will be L minus B plus 2C plus 1. You have already the values of B and C. You will get A equal 1. So means that the first group, pi 1, is L to power 1, mu to power 0. So this will be 1, DAB to power minus 1, and times KC. So this is L times KC over DAB, which is Sherwood number for with the length of L of the wall. Okay, so it's again one of the numbers, the key number we are looking for, basically Sherwood number, because it contains KC. And for pi 2 and pi 3, we have to analyze them again as we did with forced convection. So it will be m to power e and m to power 1, we get e, then t to power minus e minus f, we get e and f. E we got it from here, we got f, then from t, and then we get d from the analysis of the dimension L. So that will be like this, okay? Rho times DAB over mu. And this is the reciprocal of Schmidt number. Schmidt number is mu over rho DAB, so it is 1 over Schmidt number. And this is what we also need, okay? Or this is a common number, we know it, but just in terms of the reciprocal. The third dimension, or the third group, is obtained, okay, from this m to power h plus 1, t to power I minus h. So from here we get h minus 1, and then we get I here, and then we get g, and then sub in the equation here. The equation here, we will get this number. Get this number L cube times delta rho g over mu dAB. This is also dimensionless number, but it is not a known or a common number. So we have to divide pi 3 by pi 2 as we did with the forced convection and get this number L cube times rho delta rho g over mu square. And this one we call it Grashof number. Okay, this is Grashof number for forced convection, for Nash convection. I think you heard about it in heat transfer, right? Right?
Not yet, I guess, Doctor.
Okay, so this is Grashof number. So now for Nash convection, the three numbers are Sherwood number, Schmidt number, and Grashof number. We expect that Sherwood number should be function of Schmidt number and Grashof number, or the other way, if you want Grashof number instead, it will be function of Schmidt number and Sherwood number. Or if you want Schmidt number, it will be function of Sherwood and Grashof number. So these three numbers are related. If you go to the lab and vary Schmidt number by varying its parameters, like for example, the parameters of Sherwood number is, Schmidt number is rho, DAB, and mu. If you vary one of these, you'll vary rho, you vary Schmidt number. And here, if you vary L or the density or mu, you'll vary the Grashof number. So you go to the lab and vary Schmidt number and Grashof number, and record the values for Schmidt number, Sherwood number, and then you will establish a correlation that you can use later on to calculate Sherwood number under natural convection. And from Sherwood number, you can obtain the convective mass transfer coefficient case. Okay, clear?
Yes, Doctor.
Okay, so we'll stop here. Next time we'll do the exact analysis. So we did today the dimensionless analysis. We expect, based on the dimensionless analysis, that Sherwood number should be function of Schmidt number and Reynolds number under forced convection, and it should be function of Schmidt number and Grashof number under natural convection. Next time we'll do exact analysis of the laminar concentration boundary.